Great. So first and foremost, Kevin, would like to express our appreciation for having us here today. Super excited, and for the audience, we know it's a Friday evening, so thank you all for staying on and hanging out with us to the last presentation. But we're super excited to be here today and educate you on what we're doing here at FNN in regards to high-risk lightning and wildfires. So before I get started, just real quick, I'm the Chief Revenue Officer, and joining us today is our co-founder and CEO of FNN, Dr. Istvan Kereszy. And I'd love to start this off with a little story about how lightning became part of what we do on a daily basis. Our founder, Istvan, is a swimmer by nature, and as a child, he was often in pools, understanding why he was being delayed time and time again. And with that fascination, he made it a priority of his to understand the behaviors of lightning and why lightning is doing that. Fast forward a couple years, he had an opportunity to go to the University of Florida, which is one of the leading research labs in regards to lightning research. And during that time at the University of Florida, he received his PhD in lightning physics, which came through a DARPA-funded project. And on the next slide, I would like to kind of educate on what that looked like in the beginning, where we're going from a customer base and how the outcomes are being produced. So as many of you are probably familiar, there's some core lightning providers out there today, some international providers, some private equity-backed providers, but our goal here, and as you can see, is that we're American-based lightning provider that continues to be very focused on the mission and providing high-risk lightning data to a ton of internal and external customers. And starting that, the entire project really formed out of Camp Landing Army Base, where we were doing rocket trigger lightning. And during the rocket trigger lightning, we were able to recreate 5-mile-long channels to the size of a coin time and time again. And by doing so, we were able to understand the different characteristics of those strikes, which in turn created the long continuous current of strikes. So how does that translate into what we're doing today and what we're going to be sharing about our product and how artificial intelligence, machine learning, and the external variables take place is we've had the ability now to work throughout all of our different customer bases, whether it's through state Florida forestry services, whether it's through fire departments, whether it's through the National Guards and the DoD. And during that time, one of the things that we found out through the voice of customers, how do we operationalize lightning data? How do we understand what high-risk lightning data is? And how can we take that data and help combat wildfires? And in doing so, through our artificial intelligence and through the machine learning, we've been able to understand where those high-risk lightning strikes are, be able to compute it on the edge, return that data within 40 seconds, providing the forestry services, providing the fire department's real actionable intelligence on what high-risk lightning strikes are in that area and how they have the ability to cause potential wildfires. And in the last image, before I pass it along to Dr. Kereszy, I wanted to show you a real live situation that was recently uncovered in Montana, where you can actually see the location of the strike. And if you look really closely, the strike location is actually on that tree. And utilizing our technology, the forestry department was able to go to that strike and able to, as you can see, put it out with the hose or even just axes instead of having that fire potentially get out of hand. So how does all this happen? Well, we're excited to share a little bit more about this with you and share the additional story. And I will go ahead and pass it on to Dr. Kereszy.
Thank you very much, Kyle. Thank you for the introduction, and really appreciate the opportunity to present. Thank you for spending the Friday afternoon with us. We'll try to keep it interesting. So there were lots of discussion about the weather modeling and the data side of things, but where does this data actually come from? And that's where we, with FNN, when we did these rocket-triggered lightning experiments at the Camp Landing Army Base, we were able to collect data, a lot of data. So to give you a sense, we were able to create hundreds of lightning strikes that hit the same exact spot over and over again. And that allowed us to understand that not all lightning strikes are created equal. There are some that are very quick, the majority are very quick, and then there are some that have long continuing current, transfer a lot more charge, and their duration in terms of time is about 1,000 times longer than the rest of the strikes. And so no matter how we model the data, we couldn't get the correct input to our models from the existing detector infrastructure. So locally near Camp Blending, we started building a local network that was able to detect lightning strikes with way better timing resolution, better resolution in terms of the frequency band. So we had to employ a dual band electric field approach where we're able to separate out the extremely low frequency band. And that allowed us to understand more about the lightning strikes. Now, as it turned out, these specific lightning strikes, these high-risk lightning strikes, were also the ones that caused the wildfires. So in Florida, lightning strikes caused more wildfires than all of the other sources combined in terms of area burned. And so we started working with the Florida Forest Service on getting them actionable data. And so this is what the detector looks like. And we deployed them statewide. And that allowed us to provide real-time high-risk lightning data to the Forest Service, which, as Kyle mentioned, is something very beneficial to them. They were able to find 152 lightning-ignited fires just this year. Last year's numbers were similar, and we're still not done with the season. And so where does the AI part come in? Well, the AI part comes in through the real-time data analysis. So each of these detectors have their own solar panel, so their own power supply, and their own data upload to internet module. But they also serve as AI edge computing devices. So they have an FPGA board-based architecture, and each of these electric fields that are recorded get processed right there on the edge. And this is special because this allows us to extract all of the critical data points there without overloading the data upload. So the first part where AI is employed is really at the source where the data is collected. These detectors are placed in a grid about 30 miles apart from each other, and that's how you can get statewide coverage. Now, this is an example of upgrading an existing infrastructure, adding AI on the edge, and really delivering superior results. Another key area that we are looking at has to do with RAW stations, those remote automated weather stations that have a lot of great capabilities, and many of the forestry agencies, not just in Florida, but also out west, rely on them. But traditionally, they're only able to share data into products like MRMS once an hour. And so updating that to more frequent updates, especially for parameters like precipitation, can be critically important. Now, we find the high-risk lightning strikes, process them on the edge, then the data gets sent up to the cloud where a triangulation is performed. So from several sensors, usually at least 6 detectors within an area have to detect the lightning strike to do precise triangulation. Then we detect and locate the lightning strike down to an accuracy of 100 feet. We're able to show where the lightning struck the ground, but that's not enough. That's not enough to show the forestry firefighters where to go. They need more than that. That's where the second layer of data analysis comes in. So lightning strikes the ground, and it either causes a fire or it doesn't. And that is really the big question. On the illustration on the right, you can see the difference between the long continuing current hot lightning and the short lightning strikes. And when I hold this presentation to students, I usually ask the question, what's the big difference between the picture on the right and the picture on the left? And I always like their answer. It's pretty amusing. It's well, the house burns down. And that's really the essence. It really captures the essence that on the left-hand side, you're going to have a fire, you're going to have an ignition, and the right, you will not. So that's where the AI edge computing comes in, and the ability to process the electric field dual band electric field data is very important. But that's not all. So just because you have a high-risk lightning strike, one that's really hot, it doesn't mean that it's going to cause a fire. You also need the environmental conditions to be right. And so we have been working with Chief John Kern with the Florida Forest Service over 4 years now on understanding what are the key inputs that fire behavior analysts look at. And so 35 layers of environmental data have been integrated in the real-time analysis. So once we have the hot lightning strike and we have all of the environmental data factors, we're able to understand which one of those lightning strikes will actually start the fire. And that's where the high-risk lightning alert comes in and is sent out. One important thing is, so we talk a lot about the forestry applications, but with this application, because you have a dual band approach, you're also able to achieve superior results over land, over mountainous lands, for example. We've tested that in Montana and Idaho, and also over water, because you separate out that single frequency band into 2 bands. One band is about the location, and the other band is about the long continuing current properties. And so where are these systems deployed? Where are they making an impact? So Florida is the home base. Like Kyle was mentioning, that's where we started out with our initial installations. And here we have the Florida Forest Service. The Fire Guard program is using it, so is FPL, because it turns out that these same high-risk lightning strikes that cause the wildfires are also the one that cause all of the heating-related damages to the power infrastructure, transmission lines, distribution lines, and so on. And the other thing we're really happy about is that this year, the Weather Channel selected FNN as their official lightning data provider for this year. And so the ability to have that data and give that advanced warning to not just forestry folks, but also to a wider population has been really exciting for us. And then mentioning some of the other areas that are especially fire prone: Montana working with the NRC, Idaho Department of Lands, and then in California working with the different agencies, in Northern California near Lake Tahoe, and then in Southern California in San Bernardino County. And so these are the Northern Hemisphere installations. And then going to the Southern Hemisphere, because training the AI, training the system, it's very important to get as many data points as possible. And to be able to do that year round, we deployed on the Southern Hemisphere as well. Australia had very bad wildfires, or they call it bushfires. In 2020, they call it the Black Summer bushfires. And over 90% of the area burned were due to lightning ignition. So they asked us to install, and we installed the system near the capital of Canberra. So that whole region is covered. And then we also installed them in Brazil. And so those are the Southern Hemisphere installations. This is a video I wanted to show briefly because it talks about how the rocket-triggered lightning experiments led to these discoveries. So the AI portion is really something that's added on, but it's been almost 2 decades of rocket-triggered lightning experiments that led to where we are today. And I think for this, it's best if I share just the tab, because that way I think the sound will go through as well. And so hopefully you can see it, and then please let me know if you can also hear it.
Now let's turn to innovation, to battling wildfires. It begins with the historic rocket launch of Apollo 12 and adds artificial intelligence and a winning student project.
As meteorologist Alex Wilson explains, we need this help as wildfires are becoming increasingly common and widespread across the U.S.
3, 2, 1, 0. All engines running. Commit. Liftoff.
Seconds later, lightning struck Apollo 12. Not once, but twice. Rocket-triggered lightning research was born.
Rocket-triggered lightning is when you have a rocket trailing a copper wire and you shoot it into a target in the thundercloud. You have control over that process. You can bring lightning to that same specific spot 10 out of 10 times.
The U.S. alone sees more than 25 million ground strikes a year. Lightning-sparked fires, especially in remote areas, can go undetected for hours, even days.
It only represents about 10-15% of the fires, but 70% of the area burned. The reason is it's really hard to find lightning ignitions today with most traditional technologies. Generally, by the time you see smoke coming up from an ignition source, the fire is pretty large.
Very few strikes actually start fires. Now, thanks to those triggered lightning experiments, scientists think they know why.
High-risk lightning is a type of lightning that lasts 1,000 times longer. And it's a very rare type, so it's actually only about 5% of all lightning strikes are this high-risk lightning, extra long duration and extra high heat. Imagine you're waving your hand above a candle and you're fine for half a second, your hand doesn't feel anything, but if you leave it there for 1,000 seconds, your hand will certainly start burning.
Startup company Fire Neural Network says their new sensors can detect and report these high-risk lightning strikes. Then artificial intelligence factors in local weather and environmental conditions.
How do you compute all this data? When you have a neural network, it's able to digest all of these loads, terabytes of data, in seconds.
And the big change is that it's no longer that firefighters and fire behavior analysts have to spend hours doing this analysis, but it all happens in 40 seconds. So it's really critical to find those lightning strikes quickly, because if you find the ignitions quickly, you can put them out quickly.
Warmer, drier conditions have caused longer, more active fire seasons. It's hoped new technology like this can stop wildfires before they take lives, livelihoods, and property.
And of course, we've seen how dangerous wildfires can be recently. So we can show you that tool live and in action because we've got some lightning going on here across portions of Central Florida. So we can take a look at which of those recent lightning strikes might reach that very high criteria.
And especially in places that are in drought, this is going to be more of a concern. This will be a cool tool to use as we get into the summer months across the West when a lot of these lightning-sparked wildfires can become explosive in development. But right now, when you look at this, we're abnormally dry. We've got some extreme drought here, especially in eastern Florida. And some of those lightning strikes are in that high to almost very high risk. So the lightning strike itself, some of the data sets is detecting that they can last 1,000 times longer than the typical lightning strike, and also takes into account the ground soil.
I thought it's worth taking a look at it because it's a good summary and the visuals often help tell the story. But going back to the presentation, just a few examples of how this works. So yes, we detected the high-risk lightning strikes. It's great. We classified it. It's whether it's intra-cloud or cloud to ground. If it's cloud to ground, we went through, we looked at it, positive, negative strikes. What are some of the key charge transfer duration components that are important? Selected them, then merged them with the environmental data layer. Neural network was able to select which ones are the most dangerous. But then what happens? Then we get them to the Florida Forest Service pilots. So the pilots receive them on their ForeFlight application. ForeFlight is a Boeing company, and they are the in-flight software that most pilots use within the Florida Forest Service. And so they have a iPad strapped to their knees, and they're able to take a look at that and find those ignition points. And so when they click, it tells them which direction they have to fly for how long to get there. And when they get there, this is what they see. So for example, this was a high-risk lightning strike. They see the data points around it, and they were able to navigate there and find this fire. And then they send us back the picture in an email saying that this is a fire that was located. And this is a good example because it visually shows the fire, but sometimes they get there so quickly that it's just a single tree smoldering. And those are the real success cases, the one that Kyle was showing, for example, when it's just that single tree that you can see and it's put out before it ever grows. And so this is really the workflow around. Of course, Florida does a lot of fuel reduction, a lot of prescribed burning, but once it's the active season, it's very important to detect. So it's detected with the FNN high-risk lightning system. It's verified by the pilots, and then it's extinguished. And so that's the workflow. And this is another example. For example, this is an example of a fire that would be very hard to see. It's in the middle of a forested area. There is very little visible smoke output, yet with the system, they were able to find it. So there were 152 of these this year. So this is really the workflow, and the AI is cool because it allows them to focus on those spots that have the high risk lightning rating as the highest, instead of having to just do a general scan pattern. And often with a general scan pattern, you cannot get this close to the point, so you're not able to find those single smoldering events. And this is more about the dashboard. In the dashboard, we're able to use another approach, a segmentation approach, to find the exact location and track those wildfires. That's very important because there are hundreds of prescribed burns and an additional hundreds of wildfires. So knowing which areas have already burned are important for the fire behavior analyst, that they know that those areas are less likely to burn in the coming months. And also for us to be able to further train the model, it's important to understand that where the firefighters put the fires are not where they actually are. So they usually stop with their trucks on the road and they take the GPS coordinate, and that's what they put into the system. The fire might be, in some cases, we see a mile and a half away. So when you're training the AI, it's important to understand where they actually are. So what we do, we look through Sentinel data, Planet data, do the segmentation, and create those burn scars. And those burn scars represent where the fire actually burned. Then we find the lightning strike that's inside that perimeter, and with that, we're able to further train the system. And so this is the dashboard that the Florida Forest Service uses. And then as a closing remark, I used the example that in Florida, lightning is the leading cause in terms of area burned. Out west, also in terms of area burned, it's a very important cause of the fires, but many fires are not caused by lightning. And one prime example, I actually think of two, are the Park Fire and the Line Fire last year in California. Both of those were not lightning caused fires, but both of those had very active pyro-CB formations. And so these pyrocumulonimbus cloud formations are when the smoke gets electrified, very intensive updrafts. The smoke gets electrified. Here's an illustration. They can create very strong winds. They can create rain in some locations, but in other locations, they can create dry lightning. And so that's one of the reasons why the Park Fire grew to 500,000 acres last year, because it was fueled by these pyro-CB events. Now, a little bit south of that, the San Bernardino County had the detection system installed, and this was the first time that electric field records were recorded for pyro-CB lightning. And so we were able to work with the fire chief, Chief Muncie, on finding these high-risk lightning strikes in real time. And so the pyro-CB events created the lightning strikes outside the perimeter. And the critical thing was how to find, so the fire chief used the example, it was like an Easter egg hunt. There were hundreds of strikes. How do you find those in these very active conditions where you actually have to go? Looking for smoke is not very useful. There's already a lot of smoke. And so using this electric field-based system, the FNN system, we were able to help them down select to just a few strokes that were outside the fire perimeter that were high risk, and so they could check those out. So this was a manageable number. The original number was not manageable. It was just an overwhelming number. And so they were able to find those, and a few of those actually started fires that started to grow outside the fire perimeter, which of course is the scariest thing. Finally, you're controlling the fire. You have new ignition sites outside the perimeter. That's something to be avoided. So this was an interesting example. And they're more and more common out west when it's actually a pyro-CB event that's fueling the further growth of the fire. So these were some of the topics we wanted to bring to you today. Thank you very much for the attention. And if there are any questions, Kyle and I are happy to take them. Thank you very much.
Thank you very much from the FNN team. Really appreciate it. Any questions from anybody online? Yeah, Rowan.
Yeah, I was just curious what the main benefit is of using AI specifically for this application rather than a deterministic model. Is it like determining the discriminator between, the standard and high risk strikes?
Yes, very, very good question, there are several layers. I will go in reverse order. So of course, with the mapping of the fires, with the burn scars, it's very useful to use the segmentation model to understand where the burn scars are. It's much faster than drawing it by hand. So there's that timing aspect. The part before that, matching with the environmental data, the critical thing there is that we're able to train on years and years of lightning ignited wildfire data. So going back to the late 1990s. And so that allows us to get a solid data set that's going to be different than each eco province. So in each of the regions throughout the country, what are the ideal conditions for fire ignition are going to be very different. So some indicators for a deterministic model, one example is the Key Environment Drought Index, KVDI. It's an excellent index in Florida. It has a very good correlation with fire ignition. When there's a drought, fires are much more likely. If you take that indicator out west and you include that in your model, for example, for Montana or Idaho, they're much less useful. And so it wouldn't just be one deterministic model. It would be many, many deterministic models for each eco province. And then it would be a very, very difficult thing to keep updating that. With this system, we're able to take into account automatically the location of the fire when we do the training. So it's a much more efficient system doing it this way. So that's what we've learned, that the system is able to find the most important factors and then use them. And so that's the second part where we use the AI. And then third part, which is really, if you think about it from a lightning detection, is actually the first part, is in the analysis of the electric fields. So many systems have been trying to understand which electric fields correspond to what type of lightning strikes. And there are some key parameters, such as 0 to 90% rise time of the electric field, such as the zero crossing of the polarity. There are some key parameters to look at. But there are some very sneaky lightning strikes. And one example is most systems, if you look at large-scale national systems, if there is a seed, a compact intracloud discharge, which is actually an intracloud lightning, most of them will report it as a positive cloud-to-ground lightning. And why is that a problem? Because for firefighters, they're trained, if it's a positive cloud-to-ground lightning, a positive cloud-to-ground lightning with a large amplitude, so a high peak current, you have to go and immediately investigate it, because those are the most dangerous ones. That's the standard training. Now, if it turns out it's a seed, a compact intracloud discharge, then it's not only that it's not a high amplitude one, it's not only that it's not a positive one, but it doesn't even come to the ground. It's within the cloud. So all those resources spent on investigating are lost. And what we found is that deterministic models, looking at some of these parameters, I mentioned two, but there are several others, help determine some waveforms, but we cannot get the performance that we can get from a AI-based model. Simply, it's a much better performance. The percentage correct is much higher, and we're able to get the better classification. And that's basically the big benefit, that those false alarms, when firefighter goes somewhere and there was nothing there, they're not happy about it. So that's something we're able to reduce.
That's all super interesting. Thank you.
Thank you for the question.
Okay, thanks again to the FNN team. Any other questions? Otherwise, we'll keep moving on to just the last quick section here. Okay, perfect. Yeah, great talk, and thank you very much for your time.